Hello students, today we are going to learn the Ampere's circuital law. Okay, so what the topic today? That is the Ampere's circuital law. And we know that if we are taking any current carrying conductor, so it will produce the magnetic field surrounding it. Okay, so what the magnetic field, or you can say what the magnitude of magnetic field will be there. So to find the magnitude of magnetic field due to current carrying conductor, we will use this law, that is the Ampere's circuital law. So this law is used only to find the magnitude of magnetic field intensity. Okay, so here what the law, how to find the magnetic field? Look here, just suppose we are taking any current carrying conductor like this. We have one current carrying conductor like this, and the current which is flowing here, this is I. The current, this is I, and we need the magnetic field because of this current. To apply this law, Ampere's law, what to do? Here we will take one of the loop. Here we will take one of the loop like this. Just suppose here we are taking one of the loop like this. We are taking the loop like this. Okay, and just suppose this is the current which is uniformly distributed. It means this current will pass through whole conductor. But here we are taking one of the loop here. Okay, so here some of the current will pass. We will take what the current which is passing here. We can write IEN. EN means what the current which is enclosed in this loop, what the loop we are taking. Okay, now what to do? Just suppose here we need the magnetic field due to the current which is passing through this loop. Okay, so you should know first how to find the direction of magnetic field. So here we can find the direction of magnetic field using the right hand thumb rule. Okay, so what the right hand thumb rule? Just suppose we are taking this current is flowing like this. So according to this rule, right hand thumb rule, we will direct the thumb of right hand along the current like this, and where the curl fingers will be directed like it is towards us like this. So here will be the magnetic field. So this is the current, and here will be the magnetic field. So what the thing current is going here? So magnetic field due to this loop will come here. Here means outward, and outward is represented by dot. So magnetic field is coming outside. First thing. And second thing, what we will do? We will take one of the small element dl, which is at the loop. What the loop we are taking at that loop, and the direction of dl should be along the direction of magnetic field. Means if the magnetic field is directed outward, so what the element dl we will take on the loop, that should come outward. So here we are taking dl element along the field. Field is coming outside, so this is the loop. So here at the loop there is the element which is also coming outside. You can say what the angle between B and the DL, that is the 0. So we have the loop, we have the field, we have the element, and then one of the current which is passing through the loop, or you can say the current which is enclosed through the loop. So according to this law, this law that is equals to, if we are taking the magnetic field here B and dot dl, what the element here dl, and integration of this, that is equal to mu naught times, which is permittivity in the vacuum, and what the current which is passing through the loop, current enclosed through the loop. So here what the Ampere's circuital law? Ampere's circuital law is the line integral of magnetic field. Line integral of magnetic field is always equals to the current, or you can say mu naught times the current which is passing or which is enclosed through the loop what we are taking. This is the Ampere's circuital law. After that we will apply, or we are going to discuss one of the application of Ampere's circuital law. So what the application? So a number of applications are there, but here we will apply. In this lecture we will see only one application, that is magnetic field due to infinite length current carrying conductor or straight current carrying conductor. So look here, if we are taking, this is the current having infinite length like this, and the current is going up having value I, and we need the magnetic field here at this location. What the magnetic field here at this location? Just suppose this location is P. So what the magnetic field here? So what to do? First you will take one of the position, like this is the R from the conductor, or you can say this is the perpendicular distance from the conductor here. Now we need the magnetic field. So you should think what we started in the Ampere circuit law. How can we apply the Ampere circuit law? To apply the Ampere circuit law, first we should take one of the loop. Okay. So here we can consider one of the loop like this. One of the loop like this. We can consider the loop like this. Okay. So this is the wire, and we are taking the loop like this. And according to right hand rule, right hand thumb rule, the current is going up. So at this location the field will be along the curl fingers, means inward. So field will be inward. This is inward, and we are representing the inward using cross, which is representing the field inward. So here there is the magnetic field, and at this loop, this is the loop. So at this location we will take one of the element dl, and that will be directed along the magnetic field. So here we will take one of the element dl, and which is also directed along the field. So here if I am writing the theta, which is angle between the magnetic field and the dl vector, so theta is 0 degree, because this dl and this field both are directed along the same direction. So theta 0. Now we will apply the Ampere circuit law. What was the Ampere circuit law? Integration of B dot dl, that is equal to mu naught times. So what the current which is passing or which is enclosed through this loop, that is I. So here integration B dot dl, that is equal to B dl cos theta dot product, which is equal to mu naught times I. And what the theta, which is angle between B and dl, so integration B dl cos 0. Cos 0 is 1, and here mu naught times I. So here integration B dl cos 0 1, this is mu naught I, and here B integration dl, which is mu naught I. So here look, dl, we are taking one of the circular loop, one of the small element we are taking, which is dl. So after integration we will get the complete circle, or you can say circumference, which is 2 pi r, because the radius we are taking here r. So b into what the integration of dl, this is the circumference, which is 2 pi r. Now this is mu naught I. So what the magnetic field at any location due to current carrying straight wire having infinite length is given by B equal to mu naught by 2 pi I by r. Mu naught by 2 pi I by r. This will be the magnetic field. Okay, so this is the formula for the magnetic field due to straight current carrying wire having infinite length. So you should remember this formula as well. You should remember what the Ampere circuit law and how we are applying the Ampere circuit law. You should remember like this. Okay, so in this lecture we learn what the Ampere circuit law, what the formula of Ampere circuit law. After that, one of the application, that is the magnetic field due to straight current carrying wire having infinite length. So this is the magnetic field, B equal to mu naught by 2 pi I by r. Okay, thank you.